All right, so we're going to walk through a couple of proofs today and some examples around parallel and perpendicular lines. Now, most of you guys have probably learned these facts about parallel and perpendicular lines at some points in your math careers, but probably weren't shown why they're true or proofs as to how they actually work. Today I'm going to give you guys kind of an explanation as to why parallel lines have the same slope and perpendicular line slopes multiply to -1. So let's go ahead and start. All right, so begin with the parallel lines definition. So two lines are parallel if and only if they do not intersect. So that means there's no common points on the two lines. So these guys, yes, parallel, right? They look like they have the same slope. Now, one thing to note, when we mark lines as parallel, we usually give little arrows to signify that these are, in fact, parallel lines, just to be doubly certain that they are parallel. These two lines are not parallel because if you were to continue them, eventually they're going to meet up at some point, and that's an intersection point, so they're not parallel. Okay. All right. So how do we prove that parallel lines have the same slope? So here's our little corollary, which means it follows pretty simply from the definition of parallel, meaning they don't intersect. Now it says two lines are parallel if and only if they are distinct and have the same slope. Now this if and only if bit, this means that parallel lines are, if lines are parallel, then they're distinct and have the same slope, and vice versa. If you have two lines that are distinct and have the same slope, then you know they're parallel. That's what if and only if means. Okay, so we're going to prove, if we want to show that this is true, we have to kind of prove this in both directions. We have to look at, suppose they're parallel, and then show that they're distinct and have the same slope, and then we've got to do the converse to that, which is start with two distinct lines with the same slope and make sure that they're parallel. Okay, so proof of the direction starting with parallel and showing that they're distinct and the same slope. All right, so we start off supposing that they are parallel. So that means they don't have any intersection points, right? We've got two lines that are parallel. They don't meet anywhere. Since they don't share any points, they have to be distinct. So that means we've got the distinct part pretty easily. They don't have any intersection points, so they are distinct lines. Distinct meaning not the same. Distinct equals not the same line. You'll see why this is actually important when we get to the converse later. All right, so the hard part is, okay, so we don't know very much about these lines, just that they don't meet. How can we go about proving anything about their slopes? And so the strategy when you don't have a lot of information is you try to attack the opposite. You say, like, okay, what if they did have the same slope? Or excuse me, what if they did have different slopes? Then what happens? If they had different slopes, you're going to find that there's something bad occurs. And when that happens, we call this as a contradiction. And it's impossible for you to have a contradiction in math. Math has to be consistent, meaning there aren't any contradictions. And so since you find a contradiction, you end up showing that they can't have different slopes, so they must have the same slope, which is the opposite to having different slopes. All right, so we're going to suppose for contradiction they have different slopes. So we give those names M1 and M2. All right, then our points on L1 are going to satisfy some equation, y equals m1x plus b1, and our points on L2 are going to satisfy another equation, y equals m2x plus b2. So we've got two equations for, we have an equation for line 1 and an equation for line 2. And I have these little subscripts to just keep those m's and b's separate for each of those. Okay, so now let's try to find an intersection point. So we'll find a point that's on both L1 and L2. And then this is going to be our contradiction because they don't have any intersection points, right? It's not allowed. So when we set m1x plus b1 equal to m2x plus b2, we go ahead and try to solve this equation. So we're going to collect the x's to one side. So this means we're going to subtract m2x from both sides and subtract b1 from both sides. Subtract m2x and subtract b1. And so that moves our b1 over to the right, and it moves our m2x over to the left. And then we're going to go ahead and factor the x out from both m1 and m2, so that x gets pulled out, and we've got m1 minus m2 left. And then that's equal to b2 minus b1 over here. And we divide both sides by m1 minus 2, m1 minus m2, and that gives us x equals b2 minus b1 over m1 minus m2. And so this is a value of an x-coordinate that's on both lines. The lines are going to intersect where x is equal to b2 minus b1 divided by m1 minus m2. And you can see that this is a perfectly acceptable number because we said they have different slopes. Now if they had the same slope, what would happen here is that m1 minus m2 would equal 0 if they have the same slope. And that's bad. They have same slope. And so then you'd be dividing by 0, and that would give you a problem. But in this case, we supposed that they had different slopes, and so that's a perfectly valid number, and so we found an intersection point. And this contradicts the fact that the lines are parallel. Hold on a sec. Make this go away. This contradicts the fact that the lines are parallel, don't intersect, and so that means that the slopes can't be different. They have to be the same. So that gives us our second condition. Very nice. All right. That was a lot. There's a lot there to process. This is definitely the challenging bit, is starting here with the contradiction, trying to figure out what's going to happen if they have different slopes. So we'll go ahead and try the converse, which is the other direction of this proof next. It's a little bit shorter. All right, so again, this is what we're trying to prove. We already did the left direction. So let's go ahead and try the right direction. So that means we're going to start off with distinct and same slope. These are what we're starting with, and we're going to figure out that they can't intersect. All right, so this is the going from right to left instead. All right, so we're starting off with two lines that are distinct and have the same slope. So that means that they have some slope, m, and it's the same. And so one line is going to have an equation y equals mx plus b1, and the other line is going to have an equation y equals mx plus b2. And it's kind of important here is that b1 is not equal to b2. And why is that? Why can't b1 equal b2? Well, b1 can't be b2 because they're distinct. If b1 and b2 were the same, then you'd have exactly the same equation here, right? If these were the same numbers, say this was 5 and then this was 5, then m is the same, and so you just have the same equation and they wouldn't be distinct. So that means that B1 has to be B2. So this bit right here, let's get a color. So this here comes from the fact that they're distinct. Okay, so we're going to attack this the same way. How do we figure out that they never ever meet? So the only really way to approach this is to say, well, what happens if they did meet? What happens if they did meet at some point? So suppose that they met at some point. We're going to show that this is going to be impossible. Okay, so we've got some intersection point CD. So line, we can draw our lines in if we want. So here's L1, here's L2, L1, L2, and they have the same slope and they're distinct. And there's some point, I don't know, way out here, and its coordinates are CD, and that's where these guys meet. So somehow they both kind of like curve up to there, you know. So it's on both lines, meaning that if we plug in C and D, we plug C in for X, oops, and D in, let's give these different colors, D in for Y, so C is our X, and D is our Y, then we're going to get equations that use all of our values, D, M, C, B1, and B2. So that means D equals MC plus B1, and D equals MC plus B2. And so we can see now that this here equals D, and this equals D. So it says MC plus B1 equals MC plus B2. So these are both equal to the same thing, right? Because they both equal D. And so if we were to subtract MC from both sides, that tells us that B1 equals B2, right? But that's a contradiction, because we said that they aren't the same. So the lines are distinct, and that tells us that B1 is not equal to B2. So it's impossible for B1 to be equal to B2 and B1 to not be equal to B2. So they can't intersect. So they must be parallel. And that's how we prove by contradiction.